Welcome, students. Today, we're diving into Chapter 1, Real Numbers. But look, we aren't just going to memorize a bunch of formulas. No way. We're going to tackle this with the energy of a master detective solving a massive mystery. We're going to take some really complex-sounding ideas and break them down into simple, logical steps. So, grab your magnifying glasses and let's jump right in.
Okay, let's start by confronting the ultimate boss battle of this chapter right up front. You know how you've been told that the square root of 2 is an irrational number since class 9, right? Your teachers told you, the textbooks told you, but can you actually prove it? If someone stopped you on the street and challenged you, could you lay out the ironclad mathematical logic? Well, by the end of our time together today, you're going to be able to do exactly that.
Here is our quick roadmap for today. First, the real number universe. Second, primes, the building blocks. Third, the contradiction detective method. Fourth, proving root 2 is irrational. Fifth, tackling mixed irrationals. And finally, check your understanding. Let's get to it. Section 1. The real number universe.
Just so you know, we are grounding our entire journey today strictly in your NCERT Class 10 Mathematics textbook, so you can follow along perfectly. And hey, don't worry, you already have a fantastic foundation for this. We're basically just picking up right where Class 9 left off, taking those concepts of rational and irrational numbers, and finally, putting a solid, undeniable proof behind them.
Section 2. Primes, the building blocks.
Okay, so to prove irrationality, we first need to understand what numbers are actually made of at their very core. This brings us to Theorem 1.1, the fundamental theorem of arithmetic. Your textbook states that every composite number can be expressed or factorized as a product of primes, and this factorization is unique. Think of this theorem kind of like breaking down a complex chemical compound into its absolute base elements. You know how water is always H2O? It's unique. Well, numbers work the exact same way.
Visually, you can think of a composite number like a massive Lego castle. It looks huge and complicated, right? But if you take it apart piece by piece, you're eventually left with single, unbreakable Lego bricks. Those prime numbers, they are your bricks. The fundamental theorem basically guarantees that no matter how you take that castle apart, you will always end up with the exact same set of basic prime bricks.
Section 3. The contradiction detective.
Now that we've got our prime number Lego bricks figured out, it's time to put on our detective hats and learn a seriously powerful technique. It's called proof by contradiction. Here's how it works. We assume the opposite of what we want to prove is true. We follow the logical evidence, and then we expose the ultimate contradiction. It might sound a bit scary, but it's honestly just like assuming a suspect's alibi is true, only to prove later that it's physically impossible. If a suspect says they were in Delhi, but you logically prove their phone was making a call from Mumbai at the exact same time, boom, a contradiction. Their initial story has to be entirely false.
Section 4. Proving root 2 irrational.
And this brilliantly illustrates exactly what we need to tackle our boss battle. Let's look at Theorem 1.4 directly from your textbook, which simply states root 2 is irrational. We're going to break down this proof step by step using our new contradiction technique.
All right, here is our game plan for the proof. Step 1. Assume root 2 is rational. Step 2. Express it as a fraction, a over b, where they are co-prime. Step 3. Square both sides. Step 4. Find a common factor. And step 5. Expose the contradiction. The crucial thing here is to just follow this logical sequence carefully without getting overwhelmed by the algebra. Let's walk through it together.
We kick off our detective work by assuming the exact opposite of our goal. We assume that root 2 is rational. Now, if it's rational, it can be written as a perfect fraction. So we write root 2 equals a over b, where a and b are co-prime. But wait, what does co-prime actually mean? It just means this fraction is fully simplified. They share absolutely no common factors other than 1. This is our suspect's alibi, okay? We are assuming this fraction cannot be simplified any further.
Next up, we square both sides to get rid of that root. This gives us 2 equals a squared over b squared. Now, if we just cross-multiply and rearrange things a bit, we get 2 times b squared equals a squared. Look really closely at this. This tells us that a squared is a multiple of 2. Therefore, 2 divides a squared. And mathematically, if a prime number like 2 divides a perfect square, it absolutely must also divide the base number. So 2 also divides a.
Aha! Here's the absolute climax of our detective work. Since 2 divides a is a multiple of 2. If you substitute that fact back into our equation, you're going to find that 2 also divides b.
Wow, we just found a common factor of 2 for both a and b, completely exposing the lie of our original assumption. We assumed they were coprime sharing 0 factors, but we just logically proved they share a factor of 2. This contradiction totally destroys the assumption, proving once and for all that root 2 is, in fact, irrational.
Section 5. Tackling mixed irrationals.
Okay, the heavy conceptual lifting is done. Now we just get to apply our logic. In example 6 from your book, we need to prove that 5 minus root 3 is irrational. We're going to apply the exact same contradiction logic. Assume it is rational, making it equal to a over b. Now, by just rearranging the terms to isolate root 3 on one side, we force a rational format. That's 5 minus a over b to equal root 3. But hang on a second. We already know root 3 is irrational. An irrational number cannot possibly equal a rational fraction format, which we know is impossible. The contradiction is immediate.
Try example 7 yourself. Show that 3 times root 2 is irrational. Assume it equals a over b. Isolate the root 2 by dividing the 3 over to the other side. You end up with root 2 equals a divided by 3b. And boom, the exact same logical trap is exposed. Root 2, a known irrational number, is forced to equal a rational fraction. This proves the entire original expression must be irrational.
Section 6, check your understanding.
So looking at exercise 1.2, you now have the complete blueprint to systematically break down and prove every single one of these problems. Proving root 5 is irrational, you just follow the exact same 5-step proof we used for root 2. The mixed expressions in questions 2 and 3, just set them equal to a over b and rearrange the algebra to expose the contradiction. It's really that straightforward.
So, armed with your prime number Lego blocks and your contradiction detective skills, I highly encourage you to go crush exercise 1.2 right now. But before you go, I want to leave you with a little mystery to ponder. We just proved root 2 and root 3 are irrational, but what about the most famous number in the universe, pi? If pi is irrational, does that mean every single perfect circle holds an unsolvable contradiction inside it? Think about that for a bit. Thanks for watching, and I'll catch you in the next explainer.